So in the last episode, I generalized the product rule of differentiation, where I took k amount of functions, and if I wanted to take the derivative of their product, I would have a whole formula for that, and you can see that. I'll probably link it in the description below. Today we're going to be doing the same, but for the chain rule. So here's the chain rule that every calc student knows. The derivative of f of g of x is equal to f prime of g of x times g prime of x. Well, what if you have a composition of multiple functions? Well, students may actually come across this, but just indirectly, like the formula isn't presented. But what you would do, if you had three functions, if you had the derivative of, and so actually, again, I'm going to use f1, f2, f3 instead of f, g, and h. It's going to be kind of bland, I know, but we're going to have a lot of functions, and there could be more than 26 letters in the alphabet, so more than 26 functions. So yeah, basically we'll just we'll use f1. So if we have f1 of f2 of f3 of x, it's a lot of parentheses. 2, 3, 1, 2, and 1 too many here. Alright, so the derivative of this is going to be, well, we take our outer, so f sub 1 prime, of the inner 2, so we'll take f2 of f3 of x, right, I think, yeah, one more set here, and then we'll take our f2 prime, okay, and then times f3 of x, times f prime, or f3 prime of x. And so really what we're doing is we're taking an outer function, and then we're taking everything else inside of it, everything that comes after. And the same thing here, but we decrease it by 1, and then we decrease it by 1 until we're out of functions. So you can see this as some sort of product. But we also have a composition. We can have a composition of like 20 of these functions. And so how would we denote that? There are a few ways to denote that, and I'll probably leave that as a link in the description to a Wikipedia article on the different ways to denote this. I personally don't really like those notations because they're kind of just, they're weird. It's like R's and L's, and there are other ways, but it's just, I prefer something that kind of resembles kind of the sigma and the pi that we're used to. So I'm going to use, actually let me do it in black. I'm going to use this notation that I invented. Okay, and I know I invented it, and it's like, well, whatever. But it's just for the sake of this episode. So if we say, I'll just use a. We do a equals 1 to n of f sub a of x, I guess. This is really just f1 of f2 of dot 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 of fn of x, and then a bunch of parentheses, So this is the composition. You can actually just denote this actually fairly easily of like this. Like that, the composition of functions. That's why I chose a circle. So it's like a big, little circle, or a big circle, not a big little circle. And so yeah, it's just the composition of n amount of functions. So you can see that this is going to be useful for us because you can see, like, we'll probably have a composition of a lot of functions. So let's actually start by actually formally writing this using my notation here. So let me actually use black again. So the derivative, okay, and the way we're going to write this is we're going to use my notation, and we're going to say the composition, so we're going to do the composition, and I'll use the index I, not the square root of -1, just an index I equals 1 to n of f sub I of x. Actually, I'm going to use k, because we used k last time. Okay, so it's a bad k. So basically this is k amount of functions indexed with I, and we're going to take the derivative of their composition. Okay, and I know this is like weird notation, but think of it as like the product or the sum, but instead of that, it's just a composition. And so this is going to be equal to, well, it's going to be a product, so we can write down our product. We know it's going to be a product, so we're going to start with n equals 1, well, all the way to k, which is the amount of functions we have. And it's also the amount of terms, or not really terms, but kind of terms separated by the multiplication, you know? Alright, actually I was going a little off track. I was doing something a little bit wrong. So essentially this is where we left off with the product. And so we're actually going to take the derivative of our nth function, so fn prime, right, so we're going to take the derivative of the composition of the rest of the functions. And so we're going to have our o, and I'm going to write the o kind of like spaced out, and you'll see why, and we're going to index this m equals, well, it's not going to be just 1, it's going to be what comes after n, basically. So if n is equal to 1, we're going to start with our second term, because you can see if we take the the derivative of our nth function, that's going to be, if this is 1, if n is 1, we'll start with 2 over here, and so on. If we start with n equals 2, we'll have n plus 1, which is 3, and so on. We're going to go all the way up to k, because we're going to end at our last term. And so this is going to be the composition of these functions of f sub m of x. And I'll close that. And that should actually take care of it. That should be our entire composition. You can't really write this well in LaTeX, because, you know, you have to, I mean, you could just write it as like, you know, the little circle, and then you do a subscript m equals n plus 1, a superscript k, like that. You can't really write it like this, because it's my notation, so, you know. But yeah, this is actually really interesting. I really like kind of inventing a notation and having it apply to this, because it's kind of useless, but not really. I mean, you could have a composition of like 30 functions, and this is a really easy way to generalize this. So you take the product of the derivative of that term times, you know, composed with everything else on the inside. So this is going to start with the n plus 1, which would be 1 more than that, all the way to the last term. And that basically generalizes it. And it looks really weird, even just like this, like when we're writing the derivative of this even looks crazy, but it's just the way it is. That's math for you. So yeah, that's basically it. So hopefully you enjoyed, and yeah, I'll see you in the next episode. Bye.